Question 7 of paper 2 of June of 2024. 7.1. In the diagram, triangle ABC is drawn. AD is drawn such that AD is perpendicular to line BC. 7.1.1. Use the diagram above to determine AD in terms of sine B. So if I look at the angle of B, the sine of B is equal to AD divided by AB. So in this triangle, the opposite side from the position of B is line AD and the hypotenuse is AB. And we want to determine AD in terms of sine B. So therefore, AD is equals to AB times the sine of B. 7.1.2. Hence, prove that the area of triangle ABC is equals to a half BC AB sine of B. So the area of this triangle is half the base times the perpendicular height. And they said prove. So we'll have the area of triangle ABC is equals to half of the base, which is BC, times the perpendicular height of AD. Now, can you see we have half of BC times AD? But in the previous question, we found AD to be AB times sine of B. So therefore, it will be half of BC times AB sine of B. 7.2. In the diagram, points B, C, and D lie on the same horizontal plane. Angle ADB is equal to angle ACB, and that is equal to alpha. Angle CDB is equals to theta, and DC is equals to K units. And they give us that BD is equals to BC. 7.2.1. Prove that AD is equal to AC. So what I notice is that we have the same lengths in those two triangles and the same angle sizes and a common side. So we can use congruency, or we can rewrite the lengths of those sides in terms of alpha. So I would like to stick to trigonometry. So for 7.2.1, I would say that the sine of alpha is equal to AB over AD. So what I'm doing is I'm saying in the first triangle, or the triangle on the left, the sine of alpha is AB over AD. Therefore, AD would be equals to AB over the sine of alpha. So I'm just cross multiplying and I'm solving for AD in terms of AB and sine of alpha. Next, we can say that the sine of alpha is also equal to AB divided by AC. So in the triangle on the right, the sine of alpha is the opposite divided by the hypotenuse. So therefore, AC is equal to AB divided by the sine of alpha. And can you see that both AD and AC have the same ratios? So therefore, AD is equal to AC. 7.2.2. Prove that BD is equals to K divided by 2 cos theta. So BD is in the triangle of DCB. And we have the K there, and we have theta as well. So we know that that triangle is an isosceles triangle. That means that the angle of C in that specific triangle is also theta, and that the angle of B is 180 degrees minus 2 theta. And the reason why I want to use that information is because that will allow me to use the sine rule in order to find BD. You could have also used the cosine rule, but I prefer the sine rule. So for 7.2.2, I would say in triangle DBC, we have D is equal to C, angles opposite equal sides. Therefore, B is equals to 180 degrees minus 2 theta. And the reason would be sum of angles in a triangle. So if I set up the sine rule, I have BD, which I want to find, over the sine of angle C is equal to DC over the sine of angle B. Now we want to find BD. We know that the sine of C is equals to the sine of theta. DC is equals to K. And sine of beta would be the sine of 180 degrees minus 2 theta. So if I want to find BD alone, I'll multiply the right-hand side with the denominator. So I have K times the sine of theta over, and then I can see in this denominator that the sine of 180 minus 2 theta can be reduced to sine 2 theta. And that is the double angle for sine. So BD is equals to K times sine theta over 2 of sine theta cosine theta. And the sine thetas would cancel out. Therefore, BD is equals to K over 2 cosine of theta. 7.2.3. Determine the area of triangle BCD in terms of K in a single trigonometric ratio. So for 7.2.3, we want to find the area of triangle BCD. So in this triangle BCD, we have the length of BD and BC as the same. We know that the angle here at the center is 180 degrees minus 2 theta. And if I use those values, I can use the area rule, or I can focus on theta and also use the area rule. So I would say the area of triangle BCD is half of BD times DC times the sine of theta. So I'm choosing to use this theta and the sides of BD and DC. So in the previous question, we found that BD is K divided by 2 cos of theta. We know that the length of DC is K, and we're going to multiply that by the sine of theta. And I can put that over 1. The reason why I'm putting it as a fraction, it helps me to see the numerators and the denominators. So if I multiply all the numerators with each other, I have K squared times the sine of theta over 4 cos of theta. And you notice that sine theta divided by cos theta is equals to tan. So therefore, the area is K squared times the tan of theta divided by 4. Thank you for watching. Remember to show your support by hitting the like button and subscribing to Mathenatic.